Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on chemistry, in organic chemistry, and today we are continuing on organic chemistry. In our last lectures, what we did was that we were able to show you how to calculate for the number of double bonds, the number of triple bonds within an organic compound. We did that by showing you that to do that, you have to know how the number of hydrogen bonds that was consumed or that is consumed by any given molecule. Once you know the number of hydrogen that is consumed by any given molecule, then you will strike the ratio between the number consumed per the molecule of the compound. That is, if you are given the molecule of the compound, you divide the mole of the hydrogen consumed by the mole of the organic compound that is reacted. Once you do that, you will find for the number of hydrogen gas that is found within. You find for the once you do that, you will find a simplified ratio that will express the number of moles of hydrogen per the molecule of the compound, and then you can then use that to say that, okay, if that is the case, this is the total number of double or triple bonds within that, because we know that one double bond, okay, to convert one double bond to a single bond, you need one molecule of hydrogen gas. If you want to convert two double bonds, then you need two moles of hydrogen gas, and so on and so forth. So we did that calculation. Now today we are going to look at broad classification of organic compound. Now in our earlier video, I told you that basically we can divide organic into two parts. We can divide organic into two parts per the presence of the bond, per the type of bond it contains. Okay, we can divide it into two. We can have organic compounds. Okay, so organic compounds per the type of bond. Okay, organic compound can be classified into two. Okay, we have what we call the saturated. That's what we call the saturated ones, the saturated organic compound. Okay, and we have what we call the unsaturated organic compound. Saturated, the unsaturated, okay, organic compound. So quickly, okay, so we have what is saturated organic compound and what unsaturated organic compound. Per the presence or the type of bond the organic compound contains, we can say that organic compound is saturated. If it's saturated, then it is only having single bond. If it is saturated, then it's only having single bond. Okay, that's what we said. But if it is unsaturated, then it is having a double or a triple bond. So keep that in mind. Okay, having a double or a triple bond. Okay, double or triple. Okay, double or triple bond. So keep that in mind. Okay, this is double. Okay, so double or triple bond. Very good. So we're able to talk about that now. But today we will be talking about other classification that is not related to the type of bond that it contains. Okay, the type of bond that it contains. Good. Now generally all organic compounds are classified under this. We have what we call acyclic or acyclic organic acyclic chain, or what we call open chain. So we have the acyclic organic compounds or open chain organic compounds, and we also have cyclic organic compounds or closed chain organic compound. Now what do we mean by that? Very, very simple. What do we mean by that? We are simply talking about organic compounds where the carbon atoms are not close within a ring. We are talking about organic compounds where the carbon that are connected, okay, to each other are in a straight chain. They are opened. That means that there's no end-to-end connection. That is, there's no end-to-end connection. This and this are not connected. The first and the last ones are not connected to form a ring or rectangle or whatever. So that is what we call acyclic. For the acyclic one, generally all organic compound is either open or closed. That is what we are talking about. It's either open or closed. If it is open, it means that the first and the last, okay, the first and the last one, okay, are not, okay, connected. They are not linked. Okay, so you can have the first and the second one, and so that is it. So this is an open chain. You can see this carbon are open and straight and are not in a circular form, ring or rectangular or triangular form. They are open, okay, and they are not connected anyhow. The first and the last are not connected by a bond. If it is connected like this, then we are talking about something different, okay, and which is the next one we will be talking about. Okay, so if it is like this, if it's like this, then you can see that here the atoms will be connected end to end. So here you can't say here is first, here is last. Okay, it's closed within this rectangular form. Okay, 1, 2, 3, 4. They are all closed up, and that is not what we call the acyclic or open chain. For the open chain, they have an open carbon atoms that are not connected end to end. The first and last are not connected end to end. So basically, that is what we call acyclic. So all organic compound, you either fall here or you fall here. Now, for the closed or open chain, you can deduce from what I've said earlier that for the closed or for the cyclic or closed chain, the carbon atoms or the atoms are connected in a ring or are connected in a ring. Oh, okay, they are close or they are connected in the form of a cycle, or the carbon atoms are connected end to end. Okay, they are connected all end to end to each other. And so there is a good example here that you can see that this carbon atom, okay, there is an end to end connection. The first and last have been connected. You can't even distinguish between the first and last. So they've been connected in a ring form. So generally organic compounds, you either open up your atoms or you close up yourself. Okay, you either open or close. This is a closed one where atoms are connected end to end to each other. Okay, so basically that is it. We have that one, and we also have this. So that is what we call acyclic. For acyclic, the carbon are closed. For the cyclic, the carbon are connected end to end, or the carbon are arranged in a circular form. Okay, so basically that is what we are talking about. Now, the other term for this is what we call the aliphatic. We can also call the acyclic or open chain as aliphatic. So keep that in mind. We can also call it like that. Okay, so aliphatic one, if you have ever heard aliphatic, sometimes you can call it like that. Okay, generally they are opened. So aliphatic compounds, they are the same. The carbons are not connected end to end to each other. Okay, the carbons are not really connected end to end. So basically that is it. Now we also have, so under the cyclic one, we can further divide it into two. For the cyclic one, we have what's called the homocyclic compound and the heterocyclic compound. What do we mean by that? Very, very simple. What do we mean by that? Now, all we mean is that for the homocyclic, it means that the atoms that are connected, okay, in a ring are of the same. So same atom connected in a ring. So here they are talking about same atoms that are connected in a ring. Same atoms. So you can see here that here the carbon here and carbon here and carbon here and carbon here and carbon here, the same carbons are connected in a ring form. The same atoms are connected in a ring form. So but when you look here, for example, you can see that here it consists of what? Carbon here, carbon here, carbon here, carbon here, and then oxygen here. Okay, this makes it what we call heterocyclic. So for the heterocyclic, it consists of closed ring carbon atoms. Okay, closed ring. For the heterocyclic, they are made up of what? Different atoms within what? The ring. Okay, they are made up of different atoms within the ring. For the heterocyclic compound, they are made up of different atoms within the ring. So you can have carbon, oxygen all mixed together within the ring. Okay, it forms part of the ring. Please, it is not outside. It forms part of the ring. So when that's what we call heterocyclic. Now under the homocyclic, you can also have what we call the alicyclic one, and then what we call the aromatic one. So it's very important for us to know that. Now for the alicyclic one, you can see from here that this is an alicyclic one. So for the alicyclic one, what basically happens is that the atoms that are connected in a ring, okay, the atoms that are connected in a ring consist of, okay, it is the same atom, and it consists of what we call localized. It consists of a localized. There are no usually pi bonds there. Okay, it consists of it consists of what we call localized. Okay, the bonded electrons are localized. Okay, here the bonded electrons within that place are localized. So you can see when you say localized, they are fixed. They do not move about. Okay, so they are fixed. So here it means that they are fixed. Okay, so here it consists of what? The same carbon atoms in a ring, okay, whose bonding electrons are localized. That is, the electrons within the bond do not loiter around the molecule. It do not loiter around the molecule. It doesn't just move from one atom to another. The electrons within the bond are localized, fixed at what? At its place. Okay, they are not localized. So that is what we talk about. Okay, so basically when you say alicyclic compound, we are talking about the same carbon atoms within the ring whose electrons, okay, are localized. That is, the electrons are fixed. They do not move freely about. Okay, they do not move freely about. Now let's go to what we call the aromatic ones. Let's talk of the aromatic ones. Now when we say the aromatic ones, aromatic compounds, this time around we are also talking about closed ring carbon atoms. Okay, closed ring carbon atoms. Within this closed ring carbon atom, like this one for example, what you see is that the bonded electrons are delocalized. So here the bonded electrons are delocalized. The bonded electron, that is this one of the bonded electrons are delocalized, and these are called pi electrons. Okay, and they are called pi electrons. So delocalized, D means removed, or like not there. Okay, so delocalized. Okay, so delocalized. So here the electron, okay, so here the electron, okay, the electron inside, one of the electrons inside, okay, one of the electrons inside are delocalized. Now you can see from here that there are double bond here and there are double bond here. In every double bond there is what we call one single bond and one pi bond. Okay, in all double bond there is a single bond and a pi bond. Okay, now but you can see from here that here within this system, okay, within this system, the one of the bond that is here is a pi bond, and this pi bond, okay, loiter around. They are delocalized. They are not fixed to one particular atom. So this bond, okay, can choose to be here, choose to be here, choose to be here, choose to be here. It can choose. They can choose to be around any of the atoms at any point in time. So the bonds, okay, the electrons within these pi bonds, okay, are what we call delocalized. That form what we call the aromatic. So for the aromatic compounds, you can see that the electrons within the pi bonds, okay, that is additional bond inside, that is the pi bonds, are delocalized, are free to move. And the bonds are also conjugated. Please, that is another strong point. The bonds are also conjugated, meaning that you have here to be what? Double bond, and then the next one you get single bond, and the next one you get double bond, okay, and then you get what? Single bond, you get double bond, okay, and here we call single bond. So they are delocalized, and any of the single or double bond can become double or single at any point in time. So this place can become double, this place can become single, this place can become double, this place can become single because of the delocalization of the pi electrons within the bond. Okay, so because the electrons can move at anywhere in time, that form what we call the aromatic ones. So when you say aromatic ones, that is what we talk about. Okay, here they consist of restricted electrons or localized, okay, localized, restricted, okay, the electrons within the bond are restricted, okay, or they are localized, or what called they are fixed within the what? Within the atom, okay, or within the atom or on the atoms. But here they are free, they are delocalized, they can move, and they also consist of conjugation. Okay, the bonds, the double and the single bond are conjugated. Okay, conjugation. Okay, so they are conjugated. That's very important. Within this one too, we can also have benzoic aromatic compounds and non-benzoic aromatic compounds. We can have benzoic aromatic compound and non-benzoic aromatic compound. Now when you say benzoic aromatic compound, it strictly consists of one, this element, carbon, okay, and hydrogen. That is benzoic. It strictly consists of what? Carbon and hydrogen. So here it is only carbon. So this particular one I drew here is a benzoic one. Okay, so you can see here the atoms within the ring are strictly what? Carbon. Okay, and they are what? They are 6. Okay, also they are 6. So we can see, so we can count here 1, 2, 3, 4, 5, 6. So 6 what? Carbons, and then count hydrogen 1, 2, 3, 4, 5, 6 this. Okay, and so we can have that. But when you say benzoic, okay, the carbon atoms, okay, it only consists of carbon atoms. For benzoic, it only consists of carbon atoms within the ring. It only consists of carbon atoms. Okay, only carbon atoms are within the ring, and they are 6. Okay, and they are 6, and the double bond move around them. But for the non-benzoic one, what it means is that one of the atom can either choose to be oxygen, nitrogen, or whatever. So that's what we call the non-benzoic. So then for the non-benzoic one, the element, okay, is not necessary. The element as part of the ring is not necessarily carbon. Okay, it can choose to be nitrogen or whatever. So let me draw one of them so that you can see. So for the non-benzoic one, I can give as this, okay, that, and then I can put O here, okay, that and that. So here is hydrogen, here will be hydrogen, as usual, here will be hydrogen. There will be what? Hydrogen. There will also be what? Hydrogen. Then here will also be what? Hydrogen. Okay, there will be hydrogen. So one hydrogen for the carbon, and then the double bond will what? Will loiter around, will be conjugated. So here we have a conjugation. So you can see that double, single, double, single, double, single. So that is what it is. You can draw it in so many ways. Okay. Okay, you can draw it. You can draw it in so many ways. So you can have here. So this is what we call the non-benzoic, where the ring, okay, contains other atoms. So here I can choose to put like O over here. Okay. So when I put O over here, this time around, I've got what we call the non-benzoic. Okay. The non-benzoic. So that is what we call the classification of our organic compounds. Okay, it's very important and delicate for us to understand that. Okay. Very important and delicate for us to really understand this. Now, in our next lectures, we will be talking about what we call functional groups. Okay, we'll be talking about what we call functional group, and we'll end this lecture there. So we'll end this lecture. We'll end this lecture, that is the introduction to organic chemistry, on functional groups. Come with me. Let's have fun. Thank you.
My level, look.
It's packed.
Maybe today I don't get nothing, but tomorrow I go get something.